So the first thing to do is to come up with estimators for beta star and sigma squared. And I suggest we just look at the maximum likelihood estimators and see if that's enough to give us our pivots. So we're going to find maximum likelihood estimators. OK, so what's the likelihood? Note that x is assumed to be fixed. So it will depend on beta and sigma squared. And let me just write beta instead of beta star to signify that this is not the ground truth we're looking for, but this is a parameter that can vary here. And given what's the likelihood given y1 up to yn? This is a Gaussian, a multivariate Gaussian model. So this is going to factorize as a product over the probabilities of each of the individual yns. And each yn is essentially, you can bring this over and say that y minus x beta star follows epsilon, or is equal to epsilon, which follows a normal distribution. So what we have here is the density of a normal distribution with variance sigma squared. So normalizing factor 1 over square root 2 pi sigma squared, e to the minus 1/2 1 over 2 sigma squared, actually. And then yi minus xi transpose beta squared. And as we always do, it is often nicer to consider the log likelihood. So let us instead consider L, the log likelihood of beta sigma squared. So what happens if I take logs? The product turns into a sum. So this is going to be a big sum. So let's make a bracket here. This prefactor I can write as minus 1/2 for the square root log of 2 pi minus 1/2 log of sigma squared. And then when the log hits the exponential, it eats it up. And we end up with minus 1 over 2 sigma squared times yi minus xi transpose beta squared. In other words, I can simplify this here. There is no dependence on I, so this term just happens n times. So does the next. So now, how can we rewrite this second term? Think about what's happening here. This is a sum of squares. So in other words, I would like to write this, the prefactor is always the same, as a Euclidean norm. So this is the same as the Euclidean norm squared of y minus x beta squared. Right? So this just comes from the fact that this is just by definition. If I take a vector with these entries, then its Euclidean norm is the sum of squares. Right? So Euclidean norm squared is the sum of squares. So in other words, now I want to maximize this quantity. Note that if I want to maximize in terms of beta, these terms do not on beta. So what I'm maximizing is this one. Sigma squared is just going to be a positive number, so it doesn't really matter for the maximization here. So what I end up minimizing or maximizing is minus this term. So actually, I'm minimizing the Euclidean norm squared of y minus x beta. In other words, the maximum likelihood estimator here is nothing but the least squares estimator that you've seen in class. Let's just briefly go through the calculation again. So let's just do what I just hinted at doing. If I want to optimize with respect to beta, I take the gradient of L, and let's just omit the parameters here, of L with respect to beta. Now, I need to remember how to differentiate multivariate functions, but the norm squared has a, or the basic form. The derivative of this, if I don't care about the dependence on beta, is just going to be y minus x beta, with a prefactor of minus 1 over 2 sigma squared. And then I have to carry the map that gets me from beta to x beta, and I need to carry the derivative. And since this is the gradient, it's going to be x transpose here. OK, so in order to maximize, I would set this equal to 0, which means, I can multiply by 2 sigma squared. Oh, and I forgot a minus sign, which is not super important because we're just setting it to 0. This is actually going to be plus. So I can multiply through by this. I don't care about that part. And I forgot the 2 from the norm squared. Again, it doesn't matter because it goes away when I set it equal to 0. And what I end up with is x transpose y minus x transpose x beta is equal to 0. And this is the normal equations. And now it's important that I assumed x to have full column rank. So look at what's happening here. X is an n by p matrix. So x transpose times x is a p by p matrix. And the assumption that x is full column rank means that this is invertible. Or it implies that this is invertible. X full column rank implies that we can write beta hat, our estimator, as x transpose x inverse x transpose y. Let's write that here as well. Great. So we found our estimate for beta star. And now let's try to optimize this likelihood again with respect to sigma squared. So taking the derivative again, I'm treating sigma squared as the variable, not sigma itself. So what happens here, this term doesn't depend on any of the parameters, so it goes away. This term is minus n over 2. And then if I differentiate the log, I end up with 1 over the parameters, so 1 over sigma squared. And then this one is 1 over sigma squared. So this is like 1 over x. Differentiating gives me minus 1 over x squared. So in other words, minus 1 over 2 sigma to the 4th y minus x beta. And now I can already plug in beta hat. Or let's not plug in beta hat yet. Let's say I set this equal to 0. And then in the ensuing calculation, I'll plug in my optimal beta hat. So in here, there is no matrix algebra happening. This is a one-dimensional equation multiplied through by sigma to the 4th. Divide by n, and the 2 cancel to see. And I made a mistake somewhere. I forgot the plus sign here. So this is going to be plus sign because 1 over gives me minus. So we see that sigma hat squared is 1 over n y minus x beta hat squared. And let me call this sigma hat actually sigma hat MLE for maximum likelihood estimator, because we might have to modify it later. Remember, you might have seen the same effect already for in the Gaussian model without the linear regression, that if I write something like this, sigma hat squared is actually not unbiased. There's actually a bias, and what we'll need at the end of the day is the unbiased estimator. But the bias will basically come out of a calculation we're going to do in part 2. OK, so we have our estimators. And now we can immediately see why I was interested in estimating sigma squared. In part 2, I will quickly tell you why. Because you'll see that in order to write down a nice pivot, we'll have to normalize by sigma squared, and we need a plug-in estimator or something to estimate what that sigma squared actually is, because it's not known to us. OK, and I was slightly quick here and did not go through the second derivatives to actually check that this is a local and therefore global maximum of the likelihood. Why would it have to be global? Well, you can check that there is no boundary that could happen, or you can quickly convince yourself that there are no boundary effects, that the likelihood will go off to -infinity if you turn any of these parameters to infinity. And we only found one stationary point, right? So there were no other zeros of this expression here. But you should check that it fulfills indeed the local sufficient conditions to be a local minimum and therefore also a global one by plugging in these numbers into these estimators into the second derivatives and verify that indeed the second derivative is a negative definite, because we're maximizing something. OK, and I need to erase.